lecture, we will cover the second half of chapter 16, where we will discuss pericyclic reactions. A pericyclic reaction is a new type of reaction that we're going to look at that involves the movement of electrons in a circular fashion. There are going to be three types of pericyclic reactions. The first one is a cycloaddition reaction. In this reaction, we're going to form two new sigma bonds. It's going to involve three double bonds, three sets of pi electrons moving in a circular fashion, and we're going to break two pi bonds and form two sigma bonds. An electrocyclic reaction is going to involve forming one sigma bond and breaking one pi bond. In this case, we have one molecule that is a starting material that also results in one molecule as the product. And finally, the last molecule is a sigmatropic rearrangement. In this case, we're actually breaking a sigma bond and forming a new sigma bond. There are a few characteristics that are standard for all of the pericyclic reactions. The first, the reaction mechanism is concerted. So all of the electrons that are part of the reaction are going to move simultaneously, and there will be no intermediates that are formed throughout the reaction. The mechanism of the reaction is going to involve the electrons moving in a ring that is a closed loop. The transition state of a pericyclic reaction is going to be cyclic. And then finally, the polarity of the solvent has no effect on the reaction rate. So we're going to dissect each of these reactions one at a time, but one of the main differences between the three is the number of pi and sigma bonds that are formed and broken. In the cycloaddition reaction, we form two sigma bonds and break two pi bonds. In the electrocyclic reaction, we form one sigma bond and break one pi bond. And in the sigmatropic rearrangement, we're just going to end in the same number of sigma and pi bonds. So this is a good way for you to distinguish these reactions from each other. The DielsAlder reaction is the most famous pericyclic reaction. And this reaction is considered a 4+2 cycloaddition reaction. So 4 comes from the two the two pi bonds that are part of the diene, and the 2 comes from the two electrons in the pi bond of the other alkene in the starting material. And so we can draw out the mechanism for this reaction, and the mechanism for these is all three of these types of reactions are going to look fairly similar. We're going to have electrons moving in a ring, each two bonds apart. And you can actually draw the mechanism for this either clockwise or counterclockwise. The result is that we convert a diene and what we call a dienophile into a alkene inside a six-membered ring. We're going to focus on the Diels-Alder reaction for the majority of the rest of this chapter, as it is the most common example of a cycloaddition reaction. First, let's look at the reaction coordinate diagram for this reaction. Our starting materials, the diene and the dienophile, will have one transition state that involves all 6 pi electrons moving in a circular fashion. So we form a full ring of electron movement, and then we have a product that's thermodynamically favored, which is an alkene inside of a cyclohexane. The product of the Diels-Alder reaction is thermodynamically favored at low and moderate temperatures, but if we heat the reaction above 200, a retro-Diels-Alder reaction can occur, which involves the breaking of the two sigma bonds and the rearrangement of the electrons back into the diene and the dienophile. Let's take a look at this reaction in terms of its free energy. We're breaking 3 pi bonds and we're forming 1 pi bond and 2 sigma bonds. Because we're forming 2 sigma bonds and breaking 2 pi bonds for our overall net conversion, that's going to provide us a negative enthalpy term. When we look at the entropy, we're going from 2 molecules into 1 molecule, so we're going to have a negative entropy term overall. Since we have a negative enthalpy term and a positive entropy term, the enthalpy term must be larger than the entropy term for the reaction to be favored. And this is why we have such an importance on the temperature of this reaction. At very high temperatures, the entropy term is going to oppose the formation of the product, or even potentially take some of the product material and convert it back into the starting material. Therefore, the ideal temperature to run this reaction, to run the Diels-Alder reaction in the forward direction, is between room temperature and 200 degrees. Temperatures above 200 degrees will result in the formation of the diene and the dienophile from the cyclized product. The diene, or molecule with 2 conjugated double bonds, and the dienophile will react together with a 6-electron, 3-bond movement to form the product. The reaction proceeds at a faster rate if the dienophile contains an electron withdrawing group. And when we look in a little bit more detail at the mechanism of this, using resonance, we can understand why. When an electron withdrawing group is present on the dienophile, the reaction is going to occur spontaneously. Here are a few examples of electron withdrawing groups that are highlighted in red. For the most part, they're going to be carbonyl compounds. And remember, we have a resonance form on the carbonyl where we can move the electrons up to the oxygen and puts a positive charge on the carbon. If we draw out an additional resonance structure, we can see that we can move the electrons on the alkene up to this carbon as well and form a positive charge on this terminal carbon. All reactions, we're going to have to look at both the stereochemistry and the regiochemistry of the reaction. And so to start with, for the Diels-Alder reaction, let's take a look at the stereochemistry. Depending on which dienophile we use, the stereochemistry of the dienophile, it will directly affect the stereochemistry of the product. If we have a cis alkene, or dienophile, Z dienophile, then we will obtain a cis product. If we have an E dienophile, then we will obtain the trans product. It's also possible for an alkyne to act as a dienophile. Since we have an extra pi bond in the starting material, the product will result also in an extra pi bond in the product, and we will have no stereochemistry. There won't be any stereochemistry options in the product because there will be an alkene present, so it'll be a quaternary substituted alkene. As far as the diene starting material goes, you can recall that we have 2 potential conformations of the diene, the S-cis and the S-trans. Because we need the cyclic transition state for this reaction, it's only possible for the reaction to occur with the S-cis starting material. Any diene that is trapped in the trans conformation will not undergo a Diels-Alder. Normally, we have free rotation around this bond, which allows the trans and cis conformations to interchange. But when it's part of a ring like this, we no longer are able to rotate around that bond, and we will not get any reaction from this DielsAlder starting materials. Only dienes that are available to go in the cis conformation can do Diels-Alder reactions. There are some cyclic dienes, like cyclopentadiene, that are actually locked in the S-cis conformation. And these are going to be even better dienes for a Diels-Alder because they're already forced into the conformation necessary for our six-membered ring transition state. In this reaction here, we can react cyclopentadiene with this alkene, and the product we get is actually a bicyclic product because now we formed two new bonds between these carbons, and so therefore the fifth carbon of the pentadiene becomes the bridgehead position of the product. We can even react cyclopentadiene with itself. One of the molecules of cyclopentadiene reacts as the dienophile, and then the other reacts as the diene. And so in this case, if we have a cyclic dienophile, we're actually going to get a fused ring at this position, and also the bicyclic structure due to this carbon. When we form a Diels-Alder reaction product that is a bicyclic system, we can describe the relative orientation in stereochemistry of the groups attached to the dienophile as either endo or exo. And this depends on the approach of the dienophile. So if the dienophile approaches from the bottom, then the two groups would be oriented downwards. And if the dienophile approaches from the top, then the two groups would be oriented exo from the top. And this is relative to the bridge carbon. So endo is syn to the larger bridge, and exo is anti to the larger bridge. The endo product is going to be the major and generally the only observed product for the reaction. And this is because the approach of the dienophile to the diene. See, if the dienophile approaches from the bottom, then there's a favorable interaction between the electron withdrawing groups and the electron density of the diene. And that will lead us to this endo product. If the dienophile approaches in the opposite orientation, then the diene electrons and the electron withdrawing groups are too far apart to interact, and there's no favorable interaction. So overall, this approach, the endo approach, is going to lead to a transition state that is much lower in energy. And we can take a look at that transition state diagram. The endo product in blue here has a transition state with a potential energy that is far, far lower than the exo product. The endo product itself is actually a little bit higher in energy, but the transition state is so much lower in energy that this is going to be the major product that we absorb. It's going to form much, much quicker, and this reaction will be irreversible depending on temperature. Now let's take a look at regiochemistry. In some cases, there will be only one regiochemical outcome, and that's if we have a symmetrical diene, because then it does not actually matter the orientation of the aldehyde here, the two products are identical. If we have a symmetrical dienophile, the same holds true, where the two potential products, depending on the orientation of the diene, are going to be exactly the same. The only time we have to worry about regiochemistry of the Diels-Alder reaction is if we have a unsymmetrical diene and an unsymmetrical dienophile. So in this case, we have a diene with one substituent and we have a dienophile with one substituent. And depending on the orientation of the two, we could obtain two potential products. The major product is outlined here, and in order for us to understand that, we need to look at the movement of electrons and the resonance structures. So let's look at the resonance structures of both of these molecules. In the diene, we can move the electrons from the methoxy group to this terminal carbon, and that puts a negative charge on that carbon. In the dienophile, we can push the electrons up to the oxygen, and then ultimately resulting in a positive charge on the terminal carbon here. So if we look at the location of these two charges and orient the molecules in such a way that the negative charge directly is going to line up with the positive charge, right? Here's the partial negative and partial positive. You can see how that will lead to our major product forming faster, because the transition state of this is going to be much lower in energy due to the alignment of the electrostatic forces. We can return to our molecular orbital descriptions and look at the molecular orbitals for butadiene as well as ethylene. We have 4 electrons in butadiene that are going to occupy the 2 lowest energy molecular orbitals. We have 2 electrons in ethylene that occupy the lowest energy orbital. In order for us to react these two together, we're going to need the electrons in the highest occupied molecular orbital of one compound to interact with the lowest unoccupied molecular orbitals of the other compound. So we can have, since the electron withdrawing group is on ethylene, we can have the LUMO of ethylene accept the electrons, and the highest occupied molecular orbital of butadiene donate the electrons. So we'll have this orbital interacting with this orbital. And what that looks like is a symmetrical overlap of these electrons. We can form our 2 new bonds and our product. In this case, the symmetry of the orbitals between these two is allowed because there's overlap between the appropriate orbitals. There's another case we can look at. So DielsAlder was a 4+2 cycle addition reaction. Here's an example of a 2+2 cycle addition reaction. We have 2 molecules of ethylene, and we could draw a mechanism out where we break 2 pi bonds and form 2 sigma bonds. We can analyze the highest occupied and lowest unoccupied molecular orbitals of this reaction to determine if it's allowed via the symmetry. The highest occupied molecular orbital of ethylene and the lowest unoccupied molecular orbital of ethylene. If we try to align those orbitals, we see that it's forbidden through the symmetry. We are not able to overlap the orbitals, and so the reaction does not occur. In order for us to execute this reaction, we must use light to excite one of the electrons from the low orbital up to the second energy orbital, and this now creates a new highest occupied molecular orbital. And then when we go to run the reaction, we see now that we have 2 orbitals which will overlap, and the reaction will be symmetry allowed.